Bond order is worth talking about as well. Bond order is just nothing more than the number of bonds between a pair of atoms, and it's so easy, it's hard. This is, by the way, acrylonitrile, a molecule from organic chemistry, and what the arrow is pointing to there is a carbon-carbon single bond. Single bonds always have bond orders of 1, so that carbon-carbon bond order is just a bond order of 1. Double bonds have a bond order of 2. So if you see a double bond, write the bond order of 2. And finally, you can probably imagine if you have a triple bond, that's going to be a bond order of 3. So in this molecule, there's quite a few bond orders of 1. There's a bond order carbon-hydrogen right there. There's a bond order carbon and hydrogen there. Bond order carbon and hydrogen there. And the bond order of 1 between carbon and carbon. Then there's one bond order of 2 and one bond order of 3. Literally, number of bonds equals the bond order. Formaldehyde is given in the lower right-hand side there, and it says what's the carbon-oxygen bond order in formaldehyde. And you can see the carbon is the kind of gray/black atom, and oxygen is the red. So literally count up the number of lines between the carbon and the oxygen. I see 2 lines. That means this is going to be a bond order of 2. You can have bond orders of 1.5 and 2.5. I'll show you that in a little bit. A bond order of 0 doesn't make any sense because that would mean there's no glue, if you will, between the atoms, and the atoms would just float away from each other. So a bond order of 0 wouldn't be reasonable. The other ones we're going to see are possible. You can have a fractional bond order like the 1.5 or 2.5 I showed earlier if you have a resonating structure. So here's the resonating structure for nitrite, NO2-1. It's not nitrogen dioxide neutral, this is nitrite, NO2-1. This is diamagnetic, everything is paired, but you can see there's a choice where the double bond goes. It could go on the left or it could go on the right. So bond order for resonating forms, you take the total number of electron pairs used in that resonating bond, and you divide them by the number of places they can go. So whether you use the left or the right, there's a total of 1, 2, 3 bonds. All right, 3 lines. That's the 3 that goes right there. And those 3 lines are either here between the left and the right NO, or here between the middle and the right NO. So there's 2 places they can go. So 3 pairs divided by the 2 places they can go, this is a bond order of 1.5. Most of the time bond orders are 1s and 2s and 3s, but if you have something that resonates, then you can get into 1.5s, etc., etc. Bond order is pretty simple, but it does relate to 2 things which are really useful, and those are bond length and bond energy, okay? And formaldehyde is shown again on the right-hand side. Notice that there's some numbers that are in picometers, PM, and there's also some energies, kilojoules. Bond length is what they're looking at when it comes to the picometers. So the carbon-hydrogen bond length is 110 picometers, and the carbon-oxygen double bond, 123 picometers. But there's also some bond energy values. The 414 kilojoules is the energy to break a mole of carbon-hydrogen single bonds. It's endothermic. Bonds don't break by themselves, but if you add 414 kilojoules per mole, you'll break it apart. The carbon-oxygen double bond takes 745 kilojoules to break up a mole of carbon-oxygen double bonds. We're going to see that bond order can be related to both bond length and bond energy, which is pretty cool. When it comes to the bond length, bond length is inversely proportional to the bond order. So what that means is as bond order goes up, the bond length goes down. Or if your bond lengths are getting bigger, your bond order is going down. And that's kind of a cool thing to know. Now, for this particular problem, all right, we're looking at 3 different hydrogen with halogen molecules, HF, HCl, HI, all right? If you remember from Chem 221, as you go down the periodic table, atoms get bigger. Atoms get bigger generally as you go left and down. So iodine is a lot bigger than fluorine. And notice how the size between the hydrogen and that halogen is getting bigger. So F is the smallest bond length. Chlorine's in between, 1.310. Oh, and by the way, these are angstroms. An angstrom is 10 to the minus 10 meters, so pretty small lengths, okay? But HCl is bigger, longer than HF, and HI is even bigger yet. As bond order goes up, your bond length goes down. That's what it said on the last screen. And this is a better example to show what's going on. The upper left-hand corner is methanol, and methanol has a CO single bond, and that's 1.410 angstroms. Carbon dioxide has a C double bond O, a carbon-oxygen double bond. And carbon monoxide, lower right, has a C triple bond O. So you see you're going from a bond order of 1 to a bond order of 2, and CO down here, bond order of 3. As your bond order goes up from 1 to 2 to 3, the bond length goes down, 1.4 to 1.3 to 1.2. That's what it means. As bond order goes up, your bond length goes down, and vice versa. So think about that. As bond order goes up, your bond length goes down, and that's kind of a neat thing. So bond order 1C single bond O will be longer than a C double bond O, bond order 2, and a C double bond O will be longer than a C triple bond O with a bond order of 3.